instead of looking at how to graph simply a line, you try to find solution regions. And a lot of the time you use this for optimization and engineering. So you'll see, and I'm going to show you an example in a moment where you can see that, but if you need to maximize some sort of a parameter, like profit, where you have like 3 other parameters, like for example, your workforce, the cost of the materials, and let's see, and the number of work, well, no, and then the rate you're paying your workforce. So the number of workforce, the rate you're paying in that, and the material cost. You're going to have 3 different locations to choose from in a region. So what you'll do is you'll notice that in this section we're going to have graphs. And the graphs, instead of having a simple line as a solution, we're going to have some sort of a linear function. It's going to be either solid or dashed. And we'll understand how that works because remember inequalities with like open circle, closed circle. And you're going to have to shade on one side or the other. And then you might have another linear function and you have to shade on one side of it. And the goal in this region or this idea is to look for the overlap of 2 sets. So this bottom quadrant here, this lower region, would be like your solution set. And a lot of the time, the reason you do that is to find a point, and usually it's a vertex. It's where they end up intersecting. If you had a third function, your optimal solution could usually be any of these 3 vertices. So what you'll notice is, and assuming that we shade above the black line there, okay, shading above the black line there, but we'll see that the overlapping of the 3 regions is this triangle in the middle. And each of the vertices represent a different point of interest. One of them is usually like some sort of a maximum, and one is usually some sort of a minimum. If there are more than 2, obviously, which there will because it's some sort of geometrical shape, the third might just be arbitrary. Okay, it might be a repeated version of one of the other vertices. So the idea behind this is similar to what we did in the last section where we were graphing, but now we're graphing inequalities instead of just equations, and we're looking for overlapping solutions. Remember with the number line, how we had to shade left and shade right, we found where it overlapped for a conjunction, for an and statement? That's really what this is, but 2-dimensional now instead of 1-dimensional. If we wanted to simply graph the first function, this is a simple one because it's only 1, and we have 3x minus 2y less than or equal to 8. Approach this like a more linear function first, okay, not a linear inequality. Think about this as a linear equation instead. If this were a linear equation, what would the slope be? Inigo?
3 over 2.
Yeah. Again, negative a over b, simply 3 over 2. Remember, guys, you know standard form, you know slope-intercept, you know point-slope. There's no need to put this in a slope-intercept to find the slope. You could solve for y if you wanted to, but it's really not worth it. Just use negative a over b. Now, once we have that, we could also use the y-intercept. And you better remember the y-intercept from standard form?
C over B.
C over b. And if you didn't, all you got to do is to find the y-intercept, set x equal to 0. So just cover this up and solve it. Okay, so it's really just c over b. So it's going to be 8 over negative 2. Okay, so there's our coordinate 0, negative 4. So we can go ahead and graph this. Okay, let's go ahead and put this on a graph. Draw yourself a sketch or import a quick axis in there, either one. If you're using Notability, you can import, what are those, the stickies, right? Add a sticky note that has graph on it. So you can do that as well. Or just simply draw a quick sketch. So a y-intercept of negative 4 and a slope of 3/2. So I'm going to start down here at negative 4. And a slope of 3/2. So I'll go up 3, right? Again, I'll start at negative 4. Let me put a quick y-intercept. And then a slope of 3/2. So I go up 1, 2, 3 over 1, 2. So there's my next point right there. Okay, I could do that again if I wanted to, or I could just continue to estimate from here. Up 1, 2, 3 over 1, 2, be around here. Alright, so there's my graph. And at this point in time, you should be pretty familiar with graphing just linear functions. What's the difference though now? We have this less than or equal to sign at the top. It's not an equal to sign anymore. It nowhere says, 3x minus 2y equals 8. So what am I going to do? What am I going to do? How am I going to figure this out? How did we figure it out when we had a linear inequality where we were looking where to shade? How do we know which region to shade on that number line? We have to do something sometimes.
You test the point.
Yeah, we tested a point. Think back. We had the number line and we had these three regions, remember? And we did our graphical method with the deviation, 5 above and 5 below, and then we tested the middle and tested the outsides. So here, there's two regions really. There's the region above the line and the region below the line. Okay, again, this is region 1 over here, and this is region 2 over here. So go ahead and test the point in one of those regions. What's the easiest point to test? 0, 0. When you do that, you get 0 is less than or equal to 8. Look at the original equation at the top, inequality. You get 0 is less than or equal to 8. Is that true?
Yeah.
Sure, it's true. That means that this side where 0, 0 is should be shaded in. Remember how we did that with the number line? If when you test it, it is true, you shade that side. So to shade with two-dimensional graphs is simply to put a bunch of lines above it. Yes?
If it's just less than or greater than, does that mean that the line is dotted?
Correct. Yes. And we haven't gotten there. Yeah, good extrapolation of that idea. So remember, open circle was just a less than or greater than symbol, and a closed circle was a less than or equal to or a greater than or equal to. So this is considered to be like a closed circle, a solid line as a boundary. Had it been just less than, as Inigo mentioned, this original line that we drew would have been a dashed line to indicate that the solution set is not on the border, but only everything above the border. Whereas here, it's on the border and everything above it as well. Okay, and everything above as well. Now, another thing you could have done, had you put this into y equals mx plus b form, you would have ended up with y, and I think it would end up, you have to flip the sign, yeah, because you'd end up dividing by a negative, remember? You would divide by this negative to do this, so the sign would get flipped. But it would look like this. And if you ever put it into standard slope-intercept form, all you need to do is look at the inequality. The inequality says greater than or equal to, right? So everything above the line. Another way to do this, instead of testing, if you ever get it into y equals mx plus b form, just look at the inequality sign. If it says greater than, it's above the line. If it says less than, it's below the line. Okay, it's not obvious in the original inequality that we started with here in standard form. Okay, this is not obvious that we were shading above. We had to test the point to do that. We plugged in 0 and 0 and proved that this statement was true when 0 was plugged in, so therefore we shaded here. But we could simply look at this symbol. Greater than or equal to means shade everything above the line. If this were less than or equal to, everything below the line. But it's got to be in slope-intercept form to utilize that shortcut, if you will. Okay, it's not true when it's in standard form. Because what this is saying really is that y, the solution set, is above or equal to this function. Again, y, the solution set, meaning y, is above or greater than or equal to this function. Well, here's this function. Everything above or greater than or equal to is up here. Okay, so it's another way of graphing a linear inequality. Okay, a linear inequality. You have a system. Now, please, for this one, import some sort of a graph. Please don't just sketch this, because the intersection is important that it's right. So go ahead and, I don't know, use that sticky note or just import a graph image, whatever you've been doing for your own notes throughout the year. I'm going to import a graph real quick. What do I need? A photo, video, or file? I'll do that. Okay, I've got two different linear inequalities here. It's up to you. I mean, the second one is already in slope-intercept form, so you could graph that by that. The first one, you could use standard form or convert it to slope-intercept because it's really easy to convert. This would become y greater than negative 2x plus 1. Okay, you could do it that way. That's fine because it's easy just to move the 2x over as a negative 2x. And this one I'm going to rewrite as y greater than or equal to x minus 3. So I'm looking at these two regions. Let me see for a second. Yeah. And I want to make sure that I notice, first of all, that the first one is a greater than symbol, right here. And the second one is a greater than or equal to. So this will be a solid line, and this will be a dashed line. So I've got a y-intercept of 1, a slope of -2. So I go down 2 over 1, down 2 over 1, or up 2, left 1, up 2, left 1. That's going to be my dash line right there. And then we'll do the other one in blue, maybe. Let's see. We've got a y-intercept of -3 and a slope of +1. Up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. I'm going up 2 over 2. Same thing, obviously. And there's a solid line right there. So the graphing portion of this, you should seriously be able to do that in 20 seconds. You should be able to graph lines very quickly. Okay, we did that last chapter, but you've also seen that in middle school. You've graphed linear functions in middle school before. Now the question becomes, what's the solution set going to be? Because how many choices do I have? I don't have 2 regions anymore. How many regions do I now see on the board?
4.
Yeah, 4. So what you need to do is test both lines independently and shade them both separately and look for the overlap of the shading. So start with the red function. Okay, start with the red function there. I would personally, again, test the origin. If the origin works, then you shade below the red function. Or you simply look at the sign. This sign right here tells me greater than. And it's set up in y = mx plus b form. So if I see a greater than symbol, what should I do? What's the shortcut I was mentioning from the last example? What should I do, James? Yeah, just shade above. So it's going to be this region over here. Everything above the red dashed line. Again, you're doing this independently. You're not just testing both regions at the same time. You're testing the red one, or the red line first, the first function, by either looking at the inequality symbol as a greater than, or plug in the origin. Plug in 0, 0. You're going to get 0 is greater than 1. It's not true. Again, plug in 0, 0 into the first equation at the top right. You get 0 greater than 1. Not true. So that means the origin right here, meaning below the red line, should not be shaded. Because when you tested the origin, it was false. How about the blue one? How about the blue one? What do you got, Will?
Also above the line, because it's greater than or equal to.
Very good. Okay, greater than or equal to, so also above the line. So we shade everything above the blue solid line now. Or we simply test the origin. And when we test the origin for the blue line, it works. It works, meaning above. You get 0 greater than -3 if you test the origin in the second equation, inequality. You get 0 greater than or equal to -3. That is true. So where are they overlapping? What's the region they're overlapping, Jeff? Where are the 2 crosshatches overlapping? Yeah. The top one, the bottom one, the left one, or the right one?
The top.
Yeah, the top. So we put a capital S there. Okay, to indicate solution set. Solution set. Now, if this were an applied problem like economics, this would definitely be a minimization problem. And this vertex here where they intersect would have something to do with the minimal point. Okay, right here where these 2 functions intersect, which is, I'll put the dot in black, that's where they intersect. That point is extremely important. The location and the value of this location, meaning the x, and the value in the y is very important when you're doing some sort of application-based math with linear inequalities. Okay, this would most likely be like a minimum value, so if you wanted to minimize cost, as opposed to it being a solution where it's at the top vertex where it would be like a maximum value. Okay? All right, let's see one more example. Just one on your own and think about what the first 2 statements actually mean. Okay, the first 2 statements can maybe throw you for a little bit of a loop. The second 2 inequalities are not bad. That's what we just did. But the first 2 maybe could confuse a little bit But think about what they actually mean. Check with the person next to you, see if you're doing it right. So what school are you visiting?
St. Thomas.
St. Thomas? Cool. Nice. Play any sports or do anything outside of school, club, all this? Nice. So is there's a junior here, Natalie Vestergaard. Does that name ring a bell? I don't know. She's like so super into Irish dancing. I know she does like competitions and stuff. And is that a big community, the Irish dancing community? Yeah. Is your family from Ireland or the Irish?
My mom's from Ireland and my dad's Irish, but he's not
From there. Okay. That's interesting. Nice. What are the schools you've been visiting? Do you shadow a lot of schools when you're looking for a high school?
I'm probably either going here or this school in Westport called Staples. And I've already been to Staples last time. I think I remember shadowing.
Where's Westport?
It's in Connecticut.
Okay. Again, the second two inequalities, not bad. What do the first two mean? Can somebody help us before we go any further? What do the first two inequalities really do? Sarah?
I think it's a domain.
Pretty good. It's a domain restriction, really. And the line x equals 6 looks like what? What does the line x equals 6 look like?
It looks like a vertical line.
Yeah, it's a vertical line. So technically, at 6 and at 3, what should we have? We should have vertical lines there. Okay, and at x less than 6, it's going to be a solid line at 6, in your shape of this side. At x greater than or equal to 3, it's going to be, a dashed line at 6, jeez. A solid line at 3, shade to the right of it. So really, you're pretty much looking between 3 and 6 on your x-axis. Okay, keep going with what you're doing. I'll start putting up what it should look like. So here's x equal to 6, or less than 6. And x greater than or equal to 3 will be a solid line at 3. So what we know already is that our solution is going to occur somewhere in here. And think about it logically. Less than 6 is everything to the left of 6. Greater than or equal to 3 is everything including 3 and to the right. Well, what's less than 6 and greater than or equal to 3? It's this region right here, where I'm kind of like shading in, okay? So the solution will definitely be in there. But we have to look at our other two functions still. This one I'll simply convert right away because it's easy to do that. Y greater than negative x plus 4. The slope being negative 1, the y-intercept being 4. I'll do that in red. Here's the y-intercept right here at 4. The slope being negative 1. I'm going to go down 2 over 2 instead of down 1 over 1 to make it quicker. And this is going to be a dashed line also. And then in blue, I have the next one, which also has a y-intercept of 4. That's odd. Did I do that on purpose? Let me see. Yeah, I did. Interesting. So a y-intercept of 4 also with a slope of negative 1/2. So this line is not going to fall as quickly because it's negative 1/2 slope. The other one was negative 1. So instead of dropping with this much of an angle or this much descent, it will probably move like this. So we'll end up with a little region here we're going to look at. So negative 1/2, I go down 1 over 2, down 1 over 2, down 1 over 2, and I connect. And this is again going to be dashed as well. Okay, so that's what we've got right now. We've got these two dashed lines and these two vertical lines, one dashed, one solid, because it was a greater than or equal to symbol. And look inside of this strip right here. From 3 to 6, you have 1, 2, 3 regions. Now, you can simply look at your equations and figure it out. or you could test a point in any of those three regions in all of your equations. Testing a point here, it could be a little bit annoying, it can take a little bit of work. So let's look physically at what's happening here. This was the one that we graphed in red. I'll circle it or box it in red. So in red it says it's greater than this. So here's the red dashed line. So the solution is definitely above this red dashed line. Is it up here? Is it here? It can't be here because we know it's above the red line. Well, if the other part is above the blue line, then we'd have this region up here, meaning above the blue line and above the red line would be right here. But this says less than. So we know it's less than the blue line. So it's everything below the blue line, but above the red line. So the region of shading should be where?
And then a little triangle.
Yeah, that little middle region. And it's actually what shape? Not a triangle, be careful. What shape is this? Anyone know what shape this is? You took geometry, Inigo. What shape is this? Come on.
Trapezoid?
Yeah.
Quadrilateral?
No, it's a we'll say quadrilateral, but it could be a trapezoid. Yeah, it is a trapezoid because you have parallel bases. So this happens to be actually a
Oh, yeah, they are
trapezoid.
parallel.
Okay? It's not a parallelogram because these, the blue and the red line are not parallel, but it definitely is a trapezoid. Okay, so this happens to be a trapezoid, and that region I just shaded there is your solution set. I'm not even going to write an S tag, okay, because that's the region. And go through the work if you want to. Pick a point in this region. You know, pick the point, let's see, so there's 1, 2, 3, 4. Pick 5 comma 0. Try 5 comma 0 in every single equation. It will work. Okay, this middle region here will work. Let's see, let's do some hypotheticals. Had this been a greater than symbol, it would have been greater than the red line and greater than the blue line. What region would that have been? If it were greater than the blue line and greater than the red line, both. James?
Is that like rectangle will slot into
Here? Here?
Yeah.
Here?
Yeah.
Which one?
The second one.
This one.
Yes.
Agreed. Good. So above the blue line, if this were a greater, then it would be up here. Above the red line would be above this. Well, this region is an overlap above both. Had they both been less than, then what would the answer be? Yeah, the one down here. Okay, but what's interesting is that Sarah picked up on right away. Jot this down, please. That's a domain restriction, really. I mean, it's a linear inequality also. Right? It is an inequality still, but it's technically a domain restriction. Okay, a domain restriction. What other types of restrictions could you have instead of a domain restriction?
Arrange.
A range restriction. What would that have looked like? What would a range restriction look like? What would a range restriction look like as opposed to domain restriction? How would it change? I know Sarah knows. She had her hand up. Who else? Come on. What would a range restriction look like? How would these equations right here change if it had been a range restriction, not a domain restriction?
Would X be between 6 and
If it's still x between 6 and 3, that's a domain restriction. So a domain restriction means you're limited to a certain location along the x-axis. A range restriction is not the x-axis. Chandler?
It's the y-axis.
So what would the equations look like then? Very good.
Oh, it would be y is less than 6 and x is -3. I mean y is greater.
Yeah. So if it were written like that, right, see what we have there? Then we would have horizontal lines going through y equals 3 and y equals 6, and we'd have a range restriction, and it would be like some region right there. Okay, so you could have a domain restriction, or you could have a range restriction, and in reality, they're just simply inequalities. Okay? Again, domain and range are restricted by using inequalities. It will come up over and over again. Domain and range restrictions are made using inequalities. So this would be an interesting problem because you would have actually 4 vertices also. Let's show them in green. Okay, you'd have 4 vertices. And most likely, 2 of them would be important in some sort of an application. And if I were just looking without knowing the actual problem and knowing what they're looking for, it would most likely be this as like a maximum and this as an overall minimum. Okay, the vertices themselves are very important, especially the top and bottom ones along the y values. These 2 would probably have no significance on the problem. Okay? Any questions on this topic? Pretty easy. We just did this stuff, right? And then we just did lines. We just did inequalities recently, the shading portion of it, but with a number line. Now we, instead of having a number line, we have two number lines, right? Also known as your XY axis, two number lines. All right, that's all I have for you. Okay, feel free to take a look.